Welcome back, Geos406 students. So this PowerPoint slides and video are going to go along with your homework 6. You're going to use some grain size distribution data that were collected by prior classes who did hands-on sieving exercises in class to help you figure out different types of pyroclastic deposits from the 760,000-year-old Bishop Tuff deposits from Long Valley caldera from Eastern California. So Long Valley Caldera is located again in Eastern California. It's on the eastern margins of the Sierra Nevada mountains, and it produced the Bishop Tuff deposits during a catastrophic caldera-forming eruption 760,000 years ago. So in this map, you can see that the ash was distributed from this eruption towards the east. It covers large swaths of what is now the Midwestern United States. The Bishop Tuff is shown in this orange color on this map. The arrows show the direction of flow away from the caldera, and to the north and to the south and east. Bishop, California is located down here in the lower right-hand corner of the map. The Long Valley caldera is a plate or piston type caldera, which I explained during the last lecture. And here's a Google Earth image that gives you some of the lay of the land and some of the areas around which the deposits from the Bishop Tuff traveled. So here's the lower left inset map showing Long Valley caldera and the extent of the Bishop Tuff deposits as mapped. In the Google Earth image, you can see Mammoth Mountain here to the left, to the west of the Long Valley caldera. This is the western margin of the caldera. The Inyo Mono craters and lava flows and lava domes stretch to the northeast. They transect the margin of the Long Valley caldera, which is up here where the mouse cursor is going. The caldera rim stretches around here. Glass Mountain is located on the northeastern side of the caldera. The caldera margin comes along in here, and the southern margin is basically crosses Lake Crowley here, and which feeds the Owens River, which goes down through the Owens Gorge. The resurgent dome is here. Mammoth Lakes, the town of Mammoth Lakes, is right here where the red dot is. Okay, so Long Valley basically started off as a place in the crust along the westernmost margin of the Basin and Range where you had a pretty appreciable accumulation of basalt magma that was generated in the mantle during extension of the crust. So from Lockwood and Hazlitt, you can see this cartoon here with depth, upper mantle. Molten basalt is generated by primarily decompression melting in the upper mantle. You can get basalt gathering here in the lower crust. It feeds some diapirs that rise up and can feed basaltic cones and even more silicic vents and cones and lava flows as that magma distills in the upper crust. So accumulations of this basalt can feed a large volume of reservoir of rhyolite magma, and this reservoir of magma can basically accumulate with time. It forms through digestion of silicic crustal material that's remelted by the basalt. It forms also through fractional crystallization. The basalt magma distills and crystallizes with time, and then the separated silicic melt can go to feed a very large rhyolite magma reservoir. So when that magma erupts explosively and violently, like it did from Long Valley caldera 760,000 years ago, it forms big ignimbrite deposits, ash flows and tephra fallout. It forms a big collapse caldera that then backfills with ash flow tuffs and collapse material, collapse breccias from the collapse process. Later on, with time, you still have magma accumulating underneath this caldera. You can get small cones to form as the magma leaks out, or you can just get a buoying up. So this is inflation of the caldera floor. It's shown down here in the lower panel of this cartoon, where magma volume increase, gas volume increase, heating causing volume increase can actually reinflate that caldera floor, creating a resurgent dome. And you can get smaller leaks of magma that form resurgent domes and cones, basically from continued magmatic activity. So there's two pictures here. The top one is by Steve Brantley from the USGS. The bottom one is one that I took. The top one shows the view looking out across Mammoth, California, which is here, where all these buildings and condos are shown here. That's Mammoth Lakes. You can see this lumpy hills here. That's the resurgent dome inside of Long Valley Caldera. And the far ring of mountains along the far side, that is the eastern caldera, eastern to southeastern caldera wall of Long Valley Caldera. So it's a really big caldera. So I took this bottom photo standing on top of the resurgent dome, looking down at the Mammoth Lakes Airport and Lake Crowley. And this low rim of mountains here, shown in the dark gray color, that is the southern caldera rim. The high mountains in the background are the White Mountains, so that's across the Owens Valley, much further to the east in Nevada. Okay, so the Long Valley Caldera eruption produced large volume ignimbrite deposits, the Bishop Tuff. So we're going to go to this Google Earth image here. Here's Long Valley Caldera. I'm going to rim it with my mouse cursor again. Mammoth Lakes is here, Mammoth Ski Area, June Lake is up here. The Owens, or the Inyo Tomono chain of craters goes up to the northeast here. Lake Crowley is on the southern margin of the Long Valley Caldera. It feeds Owens Lake, it feeds the Owens River, which incised its way down through the thick Bishop Tuff deposits along in here, and it drains out into the Owens Valley down here where Bishop, California is, which I'm circling down here by the Google symbol. The Bishop Tuff deposits flowed out and down and are deposited around Bishop, California. So there's an Owens Valley gorge tour that I made in Google Earth from some photos I took during a trip with some graduate students in 2011. You can download that KMZ file and check it out in Google Earth, and you can take the whole tour. So I'd like you to do that as part of the activities for this week's class. So in Google Earth here, I've shown a map view. This is the Owens River. It has incised its way down through the Bishop Tuff, which is very thick. The Owens Gorge Tour starts at the top of the Bishop Tuff where the deposits are not welded. It goes down along this Department of Water and Power road down into the gorge at multiple stops with photos and explanations. And as you go deeper and deeper down inside of the Bishop Tuff deposits along this road, you go down through all the different welding sections through this big, thick, tuff deposit. So basically what happens when you have a really thick deposit of ash flow material, it's hot and it stays hot for a while and it compacts itself. So under the weight of the overlying ash flow tuff burden, the lowermost levels will basically recrystallize and squeeze down. So you lose any original pumice that you might have had in the original ash flow, and it basically compacts and welds itself. And the degree of welding lessens as you get up towards the top of the deposit. It scales with the length of heating inside the deposit as it's cooling slowly, as well as the weight of the overburden of those deposits. Now downstream near Bishop, California, the deposits are thinner and unwelded. So this pin here shows the location of the quarry outside of Bishop, California. That is the outcrop where the samples that were sieved for your homework module were collected, way down here in a distal unwelded part of the deposit. Okay, so in the Bishop Quarry site, you have these thinner unwelded deposits shown here. So this is a photo I took of a bunch of students from UAF and Northern Arizona University on a field trip during 2011. You can see that you've got layering at the base of the deposit. You have some massive stuff at the top, and then you've got some basically gravel and dirt overlaying that. So you're going to use in this module granulometry to decipher the deposit type. Was it a fall or was it a flow? So tephra fall deposits are typically well sorted. The grains are pretty uniform in size. So if you collect a big bag of it and you run it through a series of sieves of different sizes and different meshes, your tephra fall deposits will all tend to primarily get collected in one or two sieve sizes because they're all about the same size. Pyroclastic density current deposits, on the other hand, are typically very poorly sorted with a wide range in grade and sizes. So if you run a pyroclastic flow sample through a set of sieves, you'll get a collection of material at a bunch of different sieve grain sizes throughout. So in this site, I've divided this outcrop up into 3 major sections. Section A, shown on the bottom, is massive. It's not layered, it's pumice rich, and all the pumice fragments are about the same size. So in the field, I would describe it as a well-sorted deposit. Section B, I think you can see, looks layered. It's layered and it contains crossbeds. Section C, up at the top, is what we call massive. It means it doesn't have any layering or structure in it. Fragment sizes are a huge range, from really big clasts that you can see even in this photo here, to very, very fine ash and everything in between. So I would call this poorly sorted for Unit C. Okay, so if we zoom in here and look at a close-up, I have a former student here for scale. The bottom Unit A has these following characteristics. It's well sorted, most of the grains are about the same size. There's not much fine ash, it's mostly just pumice. It's clast supported, which means that there's not a lot of fine ash connecting the clasts, the big pumice clasts. And it's not layered, so it's massive. It's just a big collection of pumice. No layering, no cross-bedding. Suggests a few episodes of deposition. There's a few little weak, differences as you go up through Unit A here. Unit B is really different, and you can see that. You can see the layering in this photo, especially as you get up towards the top. So in this midsection of Unit B, it's stratified, which means it's layered. It shows obvious different layers of different sizes of class and maybe different colors, and maybe there's some structure to it. There might be cross-bedding, which there is in this Unit B. So it signifies a change in depositional mechanism from Unit A. Looks very different, looks like it was layered. Could this be a series of surge deposits? That's something you'll find out by doing this homework assignment. The top, Unit C, is really fines rich, which means it's got a lot of fine ash in it. But it has lots of big floating pumice in that fine ash matrix. It's matrix supported. That means that the pumice is floating in the fine ash matrix. It has some layering. It alternates between finer and coarser grain sizes, but all of the layers are poorly sorted. They have lots of big stuff, they have lots of little stuff, and everything in between. Okay, so this slide shows the fee scale that sedimentologists use to classify different sediments according to their size. Pyroclastic deposits are clastic. That means that they're fragments of rock, right? Formed from a volcano. So they're actually described and quantified very similarly to clastic sediments. So we use a fee scale for that. The fee scale is a way to classify grain size spanning a big range in sizes. So in terms of millimeters, it goes from 0.004 up to 256 millimeters. It's a log base 2 scale, which is a little bit odd, but that's why these grain sizes here are not evenly divided by tens or hundreds or 5/5. The fee scale is shown here corresponding to each class size from 8, which is very, very fine, to -8, which is very, very coarse. So the fee scale is a little flipped. The negative sizes are very coarse, the positive sizes are fine. Sediment name from clay to silt to sand to pebble to gravel to cobble to boulder. These go along with the class size ranges in millimeters according to the fee scale. Okay, so I have these different photos flashing up here. These basically show coarser grained sizes up here. These would have a smaller fee scale size, and they show finer grain size deposits at the base. These would have a smaller fee scale size.